are basically asked in cycle 1 to target the 2 equatorial candles fields, COSMOS and UDS, and to produce a data set that was maybe slightly different from what's being targeted in the other candles fields. The key thing here I'd like to stress is homogeneity. As much as we can, the fields are covered by contiguous NIRCam wave bands, and also certainly in COSMOS, but as much as we can in UDS as well, also with overlapping MIRI imaging. So most of the survey is 10-band imaging, and that differs a lot from what's available elsewhere. We got all we asked for, which was lovely. We asked for science in cycle 1, but also to provide a massive finding chart for future spectroscopy in subsequent cycles. That was one of the arguments to do this early. And that 178 hours of execution time contains 95 hours of science time with NIRCam and 100 hours of science time with MIRI. And formally, we've set it up with MIRI and prime and the NIRCams in parallel. But basically, all of it, it's a full 100% parallel program with the prime time as well. So formally, it's actually more than 100% efficient. And it turns out to be the largest of the cycle 1 galaxies proposals, and one of the 3 largest overall, I think, in cycle 1. So we've got complete broadband NIRCam coverage, and we've also thrown in the 410M medium band filter as well, and the red end of NIRCam, which is useful for distinguishing Balmer breaks from emission lines. And after a lot of agonizing, we fixed on 2 MIRI bands, the 7.7, or I've said here, 8 micron band, which is far enough away from NIRCam to make an impact, and the 18 micron band, which gives us some leverage and some color information for separating AGN from star-forming galaxies. And so because it's so sort of contiguous and organized and with maximum overlap, it turns out to give you 20 times the area of fully sampled 10-band imaging compared to the other programs. Doesn't go quite as deep as some of the GTO, but it is very even in terms of coverage. And when we run these simulations, empirical simulations, no surprise here that most of the galaxies we'll uncover haven't been seen by either Hubble or Spitzer. The other thing is, although the program reaches 29th magnitude, a lot of it is to 28 and 28.5. And actually, it's an imaging survey whose depth is rather well matched to what you can do with NESPEC if you're looking for emission line galaxies at high redshifts. The majority of the objects we'll uncover at redshift 7, for example, can be imaged detect 03 with expected equivalent widths in about an hour with NESPEC. So that's another reason to do it in cycle 1. Some of the science, most of it's fairly obvious to many people on the call. I mean, we did include the 090W filter to enable us to do redshift 7 selection. So you can see an example here of a redshift 7 galaxy. Here's the filter coverage with NIRCam, the broadbands, and the medium band there. And this just shows the way you can cycle through redshift 7, redshift 8, redshift 10, and even the waveband information you've got can distinguish a blue redshift 10 galaxy from maybe the reddest redshift 10 galaxy you could imagine. This example here is formed at redshift 15 in a burst, so it's 200 mega years old. So even within, as well as good photos edge, you actually should get some information on the ages of these highest redshift galaxies. And then adding the MIRI, we worked a lot on this to work out what the added value was, because although the NIRCam imaging gets to 28 or 29 AB magnitude, depending on where you are in the image, realistically, the MIRI imaging, even at 8 microns, only gets down to about 25.5. But it turns out that can still be crucial for red galaxies. So here's an example red galaxy without any MIRI information, but simulated with all the NIRCam information. And you can see 3 alternative SEDs, all consistent with the NIRCam imaging. We were kind of surprised that you could actually fail to distinguish even a redshift 2 galaxy from a redshift 5 galaxy with all this deep NIRCam power. But if you add the 8 micron or the 7.7 micron data in this case, everything tidies up and the truth is revealed to be a redshift 5 galaxy with reasonable redshift constraints for such a featureless red object. So if you want to tidy up dusty galaxies at redshift 2 from more passive galaxies at redshift 5, it turns out that this imaging can be really important, and the fact it doesn't get quite as deep doesn't really matter for very red objects. You can see here the estimated error bar can still do the job. We have a lot of dynamic range because we set up the MIRI imaging, but by the time you drag the NIRCam across, you get a range of depths. So you get a deep section, a medium section, and a shallow section. And this just shows the sort of numbers of galaxies we should get in this survey at these high redshifts, redshift 7 to 12. It's a log plot, so beware here. The deep bit is actually quite a bit smaller than the medium bit. But you can see here that the statistics will be impressive. So we'll be doing proper science at redshift 7 and 8 with galaxies samples about 10 times bigger than before. And even at the very high redshifts here, we'll be distinguishing the sort of thing that is currently still debated in the literature, whether galaxy evolution extends out to very high redshifts due to something approximating more luminosity evolution, or whether it dies off more rapidly beyond redshift 10 as consistent with density evolution. So in one case here, you've got over 3 dozen galaxies at redshift 11. In the other case here, you've got single figures. The other thing, of course, a number of people in the call have sweated over trying to work out the UV continuum slopes of galaxies. I guess a holy grail here is finding something with a UV slope of -3 or even bluer, which is very hard to identify with anything other than a dust-free, metal-free population. And the leverage here compared to Hubble, where you just have these 3 near-infrared bands very close together, once you get the NIRCam bands, you can distinguish quite easily a very blue galaxy from a less blue galaxy with kind of 5% error in the slopes. Mass functions, all the rage for JWST. So we can distinguish alternative mass functions at redshift 7 because we're of course doing rest frame optical infrared. And I won't go into the details here too much, but also at intermediate redshifts, you can get right down the mass function below 10 to the 10 to distinguish whether you have any quench low mass galaxies or whether it's all just high mass galaxies. And this can tell you a lot about when things like environmental quenching kick in or don't. And lots of other science. I mean, most people in the call will be able to figure out what they could do with 10-band imaging reaching 29th magnitude in the deepest bands. This will probably be discussed. The idea here is to drag MIRI and NIRCam across each other. And for the fields that we're talking about, equatorial fields, you're quite limited in the angles you can do. And so we'll observe in 4 epochs, twice in Cosmos and twice in UDS. If things go really well, we could be on Sky April, May, right at the beginning of cycle 1 for the first epoch Cosmos observations. And basically we flip it after 6 months so we can drag MIRI across where NIRCam was and vice versa. And these are what the coverage maps look like. This is a bit busy for this kind of call. It's sort of tidier in Cosmos. It's slightly more difficult in UDS because the UDS is a kind of east-west field. And I'll just leave that up to finish. You can see here, if you look in detail, what I said about MIRI, it gets to about 25.5, whereas NIRCam gets to 28.5, 29. And overall, we have about 220 square arc minutes of overlapping MIRI and NIRCam imaging from this survey. And I'll leave that up because there's details there and stop there, Steve.
Great, thank you, Jim, very much. So we'll take just a very short pause to give people a chance to write their questions. And when you're ready, Steve, you can ask the first one.
Yeah, we have one anonymous question, so I'll jump ahead and ask this one. I think this is a question for both Jim and Jehan and Caitlin. Where there is an overlap, I guess, for the Cosmos field, do you plan on incorporating each other's data into your public data releases?
Well, I can, from my point of view, the answer is yes, but the impact in terms of depth with the more limited filters in Cosmos and the slightly, what we haven't looked at carefully really is where the strips of MIRI imaging in the Cosmos strategy, where that overlaps with here. We will incorporate it, but the impact in the overall depth here will be fairly minimal.
Thanks.
Only question so far. See if any others pop up quickly. Guess I can ask a quick one, Jim. So you probably have a number of different observing windows because you have different epochs and multiple fields. When do you think your earliest public data release will be?
Well, I think it will be towards the end of the cycle, because it's not until the end of the cycle that we'll get the overlapping imaging from, I mean, it'll kind of start off as a separate NIRCam and MIRI data set, and then therefore we'll kind of analyze that separately and produce draft catalogues separately there. The plan basically is to try and do an early data release to the consortium to see how we're getting on, if the data quality is matching up, but to do a data release fairly shortly after the finish of cycle 1, as soon as we've got the full overlapping imaging in both fields. But of course, the raw data will be instantly publicly available to anyone who wants as soon as it comes off the pipeline.
Great. Okay. Well, we don't have any other questions, so thank you very much, Jim, for sharing Primer with us.
Okay, thanks, Steve.
Yeah. And our next speaker is Madeline Marshall. We're about 1 minute ahead of schedule, so we'll get your slides up, but then we'll just hang out for a minute. That's okay, Madeline?
Yeah, sure.
Just in case people are popping in and out for specific talks, we want to make sure we stick on time. All right, I think it's time. So our next speaker will be Madeline Marshall. We'll be talking about unveiling stellar light from the host galaxies of high redshift quasars.
Yeah, hi. So my name's Madeline Marshall. I'm a postdoc here at NRC Hertzberg in Canada. And so today I'm going to tell you about what we think JWST will see when it looks for the host galaxies of high redshift quasars. So in the local universe, there are very tight correlations between the property of a supermassive black hole and its host galaxy. So here we have the very famous black hole mass to bulge stellar mass relation. And we're not entirely sure why these relations exist. And so one of the best ways to understand this is to look back in time and see whether these relations existed in the early universe. So if we look at accreting supermassive black holes or quasars in the local universe with the Hubble Space Telescope, this is what we see. So you've got a very bright point source at the center of the galaxy, which is your quasar. You can still see the very extended host galaxy emission. And so from this, you can measure the stellar properties of the galaxy, like its stellar and bulge mass. So things get much trickier though when you go to higher redshifts. So here again, we've got images with HST. So this is WIFC3. And so this is a redshift 2 quasar. So on the left, this is what you get when you observe the quasar. And so you can see there's a very weird looking shape. And so this X shape is the point spread function or PSF of the telescope. And this is just what how the instrument registers one point source on the sky. And so this weird shape is the quasar itself, but there is some underlying host galaxy emission, which is being obscured by that quasar light. Now, if you do very detailed modeling of that PSF, you can subtract off that quasar light and see what's left underneath. And so in this case, you can see this very extended host galaxy emission. And so unfortunately though, so this works well at intermediate redshifts, but as you go to the highest redshifts where we know quasars to exist, about redshift 6 and 7, we do, so this is the same instrument, exact same analysis technique. You do the PSF subtraction, and unfortunately we're left with no statistically significant detection. Now this is because as you go to higher redshifts, galaxies are much smaller, and so they're not resolvable now compared to that, the very bright quasar PSF. Now, it's not that there are no host galaxies there. We can actually look at different wavelengths, so particularly the rest frame far infrared with ALMA. And so we know these host galaxies are there. It's just a case of not being able to detect them because of this extremely bright quasar that's in the way. So at the moment, we cannot detect the host galaxies of high redshift quasars in the rest frame UV, which traces the stars. And so we haven't been able to measure their stellar masses or the high redshift black hole to stellar mass ratios. But that hopefully is about to change with the launch of James Webb. So this will cover the rest frame UV and optical emission of these galaxies. And so by having now the optical coverage, we hopefully will be able to see some of the emission lines from the host galaxies. But also we should hopefully be able to detect these in photometry as well, because with the massive collecting area of James Webb compared to Hubble, it will have a much better resolution. And we hope that we'll now start to actually be able to resolve these host galaxies from that very peaked quasar emission. So questions that we've been having very recently are, will JWST be able to observe the host galaxies? And what will the best photometric observing strategy be? So to answer these questions, I've been using the blue tide simulation to test that observational PSF subtraction technique on mock JWST images. So blue tides is a hydrodynamical cosmological simulation designed to study rare objects in the early universe. And so here is a zoom in on a couple of galaxies that have been formed in the simulation. Now, because it's an extremely large volume simulation, which is what is needed to have these very rare quasars. It's only been run down to redshift 7, but we can study the redshift 7 population. And so there are 22 SDSS-like or bright quasars in the simulation at redshift 7. And so they are the objects that I'll be talking about for the rest of this talk. So with these quasars, we make mock images of them with the SynthObs software. And so we make mock images in both HST and JWST. And so we take these mock images and then we pass them into the observational PSF modeling pipeline that we use for our HST images. And so this pipeline has no knowledge of the real underlying galaxy distribution is. All it knows is that these are images from the telescope. So here is one of kind of the main results. So here we have a quasar that's imaged in our mock HST at the top and JWST at the bottom. And so these are in the same wavelength, so about 1.6 microns, exactly the same exposure time of 4.8 kiloseconds, which is about 2 orbits with HST. So the left image is what you get when you look with your mock telescope. So you've got that very extremely bright quasar. So after passing this through the PSF subtraction technique, we get these images here. And so with this, we can do statistical analysis to see whether that host galaxy was successfully detected. And so in this case, there was no successful detection in HST, but there was for JWST. Now, because this is a simulation, we can actually make an image of what the galaxy would look like if there was no host galaxy. And so you can see the image here. And so what we see is with the JWST image, we're seeing the so this yellow emission on the left-hand side from the host galaxy, but we are corrupted by a little bit of leftover flux from the quasar in the center. So doing this for all 22 of our SDSS bright quasars, we see that HST can detect none of them, while JWST can detect 10 of them. So we're seeing that JWST should be able to actually see these host galaxies for the first time, which is very exciting. But we're not stuck with that observational strategy that was used with HST. We can look at different exposure times. So this is one quasar with different exposure times in the top panels. And then we can look at the different filters. So we've focused on the near-cam broadband filters here. We've also looked at a couple of the MIRI filters as well, which I'll mention in the next slide. So here we plot the fraction of successful detections as a function of wavelength, and I'll slowly step you through this. So first of all, if we consider the purple points here, these are the near-cam wideband filters in 10 kilosecond exposures. And so you can see that particularly for the long wavelength near-cam filters, this performs extremely well. So we're detecting more than 85% of the host galaxies of bright quasars, which is just very exciting. The short wavelength filters perform slightly worse, but still a lot better than the HST images, which detect none. So if we now consider the same filter but different exposure times, so we've got 1, 2.55 and 10 kilosecond exposures, we see that we really need about 5 kilosecond exposures or more to detect the majority of host galaxies. Now, finally, we also consider MIRI, and so we find that unfortunately, even 10 kilosecond exposures with MIRI will result in less than 30% successful host detections. So we have made all of these detailed predictions about what we think JWST will see and what the best observing strategy is. And so that guided our JWST Cycle 1 proposal, which we were very lucky to be successful. So we have 16 hours to observe 2 Redshift 6 quasars with the aim of detecting their host galaxies. So we hope to characterize the rest-frame UV and optical properties of these hosts for the first time, measure the black hole stellar mass ratio for high redshift quasars in the early universe, compare the stellar properties from JWST to the gas properties that have been measured with ALMA, and also study their environments. So this is going to be very exciting, and we're hoping that it will actually show us these host galaxies for the first time. But we're not the only people that are going to be looking at high redshift quasars with JWST. So I've made a compilation of all of the Geo programs that will be targeting high redshift quasars. And so we've got each of the different instrument modes highlighted in different colors here. So you can see kind of trying everything. NESPEC IFU, though, seems to be a very popular strategy for trying to understand these really exciting and extreme systems. So that's the Geo. And then there's also a lot of guaranteed time observations, which will observe these objects. And so overall, this is going to be a very exciting time for high redshift quasar science. So to summarize, I've been using mock images from the Blue Tide simulation to test PSF subtraction on JWST images to see if JWST can detect quasar host galaxies. The answer in short is yes. So we find that more than 5 kilosecond exposures with the near-cam long wavelength filters should be the most successful strategy and should detect the majority of quasar hosts. So these predictions guided our JWST Cycle 1 observations, which hopefully will detect 2 of these quasar host galaxies. But overall, there's going to be, I've counted 418 hours in JWST Cycle 1 dedicated to high redshift quasar science. So this is an extremely exciting time to be involved in this area. And hopefully, if there's a SAZERAC conference next year, we might start to see some of the first results. So stay tuned, and it's certainly a very exciting time.
All right, thank you very much. So we'll have some time for questions. We'll wait a little bit for people to type them, although we've already got a few. So maybe when you're ready, Steve, you can ask the first one.
Yeah, I was going to say we're kind of inundated with questions already. So have you looked at how accurate stellar masses and I guess other physical properties are in your simulated James Webb galaxies?
Yeah, so masses, no, we haven't gone that far, but magnitudes and radii particularly. So one thing that will be an issue and needs to be very carefully considered is any residual quasar flux. So if you take account for that, you can actually get very accurate measurements of the magnitudes and extents of these objects. Morphologies are going to be trickier because of that central region being contaminated, and also because the signal to noise will be quite low. But yeah, it actually is, it seems like it will do a really good job. So there's a whole section in the paper about that if you're interested in taking a look.
Thank you. So the next question was about the specific quasars that are going to be observed and the observations you talked about. Do you know, can you comment about what's known about the large scale structure around those two quasars?
So we've picked these. So we observed these with HST and have done the detailed PSF subtraction for those. And we found that one of them actually has very nearby potential companion galaxies, which is part of the reason we're interested in looking at this one. Whereas the other one, certainly in its local environment, seems to be more isolated. So it seems like it's not potentially an ongoing merger. I don't know about their larger scale environments, but certainly we've picked kind of one from each of the local environments.
Great, we have some more questions. So what do you think are the prospects of deconvolving the AGN and the host with the rest frame optical spectroscopic data, for example, using the IFU or the GRISM? Would you expect the contrast to be smaller or larger compared to the continuum, i.e. the broadband imaging?
Yeah, it's a good question. I think with the GRISM, I think things will be easier because you've got the very strong line detections. I think the PRISM, it will be tough. I'm thinking potentially one way of going about this is to basically make broadband images from the PRISM and do the same kind of technique that we're doing with our raw broadband images. But yeah, things get smeared out a lot more with the lower resolution spectra. So I think that might be tougher, but we're still hopeful. I mean, there are certainly a lot of teams targeting this, and basically we're trying every strategy that there is. So I think if it's possible, one of us will see these. So yeah.
Great. We've got time for one more question, which I had here. So about the simulations, do you apply any spreading to the particles before applying the PSF? If so, how do you approach that for each particle type?
Yeah, so these images are from, so just the stellar particles. And so that is, the images are smoothed, and then it's also then convolved with the PSF of the instrument. And then there's noise added, both shot noise and sky noise. Yeah, I can give you more details in the Slack.
Okay, great. Thank you. Yeah, and there are a number of other questions in the Slack. So
Sure.
if you want to head there after this session. Thank you very much. Yeah, thank you very much, Madeline. We will get ready for our next speaker, which is Stefano Carniani. If you want to share your screen, Stefano.
Okay, I think you see it.
Yes, I do. We can probably go ahead and get started. So Stefano is giving a talk from the NESPEC GTO team called Probing the Epoch of Reionization with the most extensive Cycle 1 JWST NESPEC program.
Okay, thank you. I would like to organize for these nice conferences. I'm Stefano Carniani. I'm postdoc at the Scuola Normale Superiore of Pisa. And in this presentation, I'd like to give you just a general overview about the NESPEC GTO program and what we are going to do in the first cycle of GWST. Okay, yes. So part of the program is also be done in collaboration with the NIRCam team. And currently, both teams count more than 50 members. So the result, the slide that I'm going to show you now are from the work from this large and growing group. Here, I'm going just to talk about the NESPEC part. I think the NIRCam part will be discussed by Brent. And as you can see, in the GTO program, we cover different topics, but most of the time is dedicated to the galaxy assemble. In particular, we're going to use the integral field spectroscopy mode and the multi-object spectroscopy mode to study the galaxy evolution across the redshift. So I just start from the MOS mode. So I think you already know how it works. So the idea is to use the 2050 100,000 shutters in the multi-shutter array to target our galaxy, redshift galaxy, and get their spectra in just one shot. In the GTO program, the idea is to use 3 shutters for each target, and then we adopt the nodding scheme to subtract the background emission. Okay, you can see the example in the bottom figures. You can see the 2D maps before and after subtracting the background emission. And this scheme is mainly used for the survey, very high redshift, higher than 5. For the surveys targeting lower redshift target, lower than between 1 and 5, we are going to use 5 shutters to take into account that the extensions of the galaxy and to study the emission along the Y direction. Just to give you an idea what we can do with 3 shutters, this is one simulation targeting the ultra deep field. In one shot, we can observe up to over 200 galaxies with the prism. And some results you can find in the paper Bachelard 2019. Here you can see the 1D spectra. If you observe this field for about 28 hours, so you are able to probe to observe galaxies with very low star formation rate, about 1 solar mass per year, that represent the bulk of the galaxy population. These are redshifts. You can see the continuum with high signal to noise. The tutorial, we're not interested all in the prism, but we're going also to use the grating, both R1000 and R2700. Here you can see the count rate map for R1000. So we use the same mask of R100 because we want to use the observation with the grating mainly to study the nebula lines. So we don't care about overlapping spectra because there are not so many emission lines. So once that we have the redshift from the prism, we are able to disentangle the emission from different targets. About the surveys, in the MOS program, we have 3 surveys: the deep, medium, and the wide. The deep and the medium are done in collaboration with the NIRCam GTO team, and the survey is called JAGE. And here, the main goal are very high redshift galaxy, higher than 9. But in particular, we're going to observe all galaxy redshift higher than 3 to study their properties, the emission lines, and so on. As I said, the program will be done parallel with NIRCam. So you can see already seen this figure in previous presentation. So the idea is to have a pre-imaging with NIRCam and then a follow-up with the NESPEC. Just to show you a general idea, this is the scheme that we are going to use for the good south. So initially, we observe with NIRCam. NIRCam will be the prime instrument, and with NESPEC, we observe galaxy selected with by HST. Then we follow up with NESPEC to observe. So once that we analyze the NIRCam observation, we select, we make our MSA mask by using the NIRCam observations. Then we have the wide survey. This is it's not in parallel, but this is just based on current catalog, particularly it's based on HST catalogs. And the idea is to have a very large survey, 31 pointings, to reach a large number of galaxies of target. Here, mainly we are going to select galaxy between redshift 1 and 5. And as I said at the beginning, we are going to use 5 shutters because we want to study the line kinematics along the y-axis. Here you can see the number of targets as a function of the sensitivity in the prism at 2.5 micron for the 4 surveys. The medium, I split the medium in 2 programs, and within the brackets you can see the exposure time for the prism and for the grating. So in total, we are able to observe more than 10,000 galaxies. For the medium and for the deep survey, we are going to use the prism and the 3 bands at R1000 to cover all the wavelength range between 0.6 and 5.2 micron. And we are going also to use the R2700 in band 3 just to observe to study the H alpha line. While for the wide, we're going to use the prism and the tube bands at R2700 to start, as I said, to study the line kinematics and the properties of the nebular lines. So this is what about the MOS. As you can see from the figure, we have also several hours for the integral field spectroscopy mode. In this case, the idea is to study the properties, spatially resolved properties of a Redshift galaxy. For the cycle 1, we already selected 43 galaxies between Redshift 3 and 9.1. We saved several hours also for the cycle 2. And generally, we are going to use R100, R2700 to study both the stellar emission and the properties of the interstellar medium. And we are going to target both star-forming galaxy, normal star-forming galaxy, and AGN host galaxy. At redshift higher than 5, say 6, we for star-forming galaxy, we mainly select a galaxy already observed with ALMA, since the synergy between these two facilities allows us to obtain, to fully characterize the properties of this redshift population. With ALMA, we are able to study the cold, gas, and the dust emission, while with GWST, we are going to probe the emission of the warm gas and the emission of stars and their distribution in the host galaxy. So, but in general, with the GTO program, with the extensive program, we're going to study the evolution of galaxy at a redshift, in particular redshift higher than 2, where so far we have only little information, we'll say little from a spectroscopical side. So indeed, most of the observation done so far at a redshift have been done by imaging, and a few targets have been observed with ALMA or by UV emission lines. So one of the main topics of the program would be baryon cycle and the metallicity, and studied within the epoch of ionization. So far, with optical lines, we know very well the relation up to redshift 5, and we have some studies that use ALMA redshift higher than 7, but these suffer by large uncertainties and the low statistics. Another important thing is about the kinematics of the gas. So a lot of things have been done at low redshift, and recently with ALMA it seems that the gas is less turbulent, what we expect from low redshift observation. However, we cannot compare ALMA observation with the ground-based observation as like Symphony or CHEMOS, because they trace different gas phases. One, with the alpha, we are going to trace the warm ionized gas, while with ALMA, we mainly trace cold gas. So the idea is with the GTO, to extend the work up to a redshift, even at redshift 7, and see indeed if rule out or support the current scenario suggested by ALMA observation. Then still about kinematics, the idea is to study the outflows. With the depth of our observation, we're able to see the broad components, both in star-forming AGN host galaxy, and to study also the presence of outflow in faint star-forming galaxy by using the stack technique, to be one of the large sensors at a very high redshift. And with IFS, we can also see the first evidence of feedback, in which we expect to see star formation, the region of star formation, of ongoing star formation, anticorrelated with the outflow region. Still about feedback, the idea is to also to see we expect also to see a lot of passive galaxy. This is a recent work by Santini 2020. We expect in JADES to observe at least 10th galaxy with the prism. So a lot of scientific objects. So we want to do with GTO. So I've just described some of them. So I just go to the conclusion. So we have 3 surveys with the MOS, more than 900 hours. We observe more than 10,000 galaxies. Currently, for the cycle 1, we are going to observe 43 galaxies with the IFS mode, and some of the field will be delivered with the high quality spectrum. Still, we don't know which one, but we will deliver the list soon. Okay, thank you.
All right, thank you very much, Stefano. So we'll wait a little bit to give people time to write some questions.
So I might jump in and ask the first question that we've got here. I think that actually Brant has maybe just answered the question. The question was, can you say a bit more about the timeline for public release of the data? And I think Brant has answered that in Slack, saying the public release timeline for JADES depends on the scheduling. I can address this in more detail.
Okay, yes. So what I can say about the NESPEC part, so what we can do is just to won't deliver also the fully calibrated data, so the spectra fully calibrated, both for the prism and for the grading, at least for a few fields.
Okay, there's no other questions, but I will ask one. I sort of maybe have an idea of the answer too, but I'm just curious what your plan is. Do you plan to update your target list sort of until the last minute, or do you think you all are pretty set with which sources you're going to put slits on?
Okay, for the MOS, so the idea is depending on the shadowing. So the position angle strongly limit our choice, our selection. But however, the priority list more or less is already defined. So, and for the IFS, at least for the cycle 1, everything is already plan is already scheduled. So for the cycle 2, we have to plan, we have to schedule in the next month.
Okay, all right. Well, thank you very much for this great talk. And if you have more questions for Stefano about the NESPEC program, please put them in Slack and he can answer them there. We will move on to our next speaker, who is Christina Williams. Christina, would you like to share your slides?
Yes.
All right, and Christina will be talking about the Panoramic Survey. I'll let you read out your acronym, Christina, when you're ready.
Thanks. Yeah, thanks for the opportunity to talk about this survey. Panoramic is a pure parallel wide area near infrared legacy imaging survey with JWST for cycle 1. We are a small international team led by myself and Pascal Oche. And the motivation for Panoramic is to create a wide area tier for cycle 1, specifically to look for rare and red galaxies that require spectroscopic follow-up at 2 to 5 micron. And so the early discovery of objects like this is critical because given the finite lifetime of the JWST mission, finding these galaxies early means we can then follow them up in the limited number of cycles afterwards. Our pure parallel observing strategy is a really efficient way to map large areas without using a lot of telescope resources. And in addition to that, it also maps large or uncorrelated independent areas, which is really important for minimizing the uncertainties from cosmic variance for rare objects that we're targeting. So this is an overview of the panoramic survey design. So we are going to map out 150 independent near-cam pointings. So that adds up to about 0.4 square degrees. So this is 4 times what would have otherwise been mapped by the GTO plus the ERS deep field survey areas. We defined a minimum pure parallel requirement to be assigned a pure parallel observing slot. So that was, we wanted 1 hour of science integration split over 6 broadband filters, which is, ends up being roughly 20 minutes per filter. So we get depths in the range 27 to 28 magnitude AB 5 sigma point source limits. So not all of our pure parallel slots will be only the minimum. Some of them will be longer pure parallel visits. And so when we get visits that are longer than 2 hours, we plan to add in the 4.1 micron medium band filter, which will help us to improve our photometric redshift performance. And an important part of these pure parallel observations is that there's no proprietary time. So this means that our data is public immediately, and this sort of enables community follow-up of targets that are discovered in the panoramic imaging as early as cycle 2. We expect that by cycle 2, the cycle 2 deadline will have something like 20 to 30% of our imaging already taken. But for sure, all of our imaging will be ready for the cycle 3 proposal deadline. So this survey design enables breakthrough science by discovering currently unknown rare and red galaxies. So this splits into roughly 2 different science cases. So science case 1 is to look for the first star formation in galaxies forming at cosmic dawn. So this plot on the left is showing our 6-filter minimum survey design with some SEDs for galaxies above redshift 9. And so what you see is that our NearCam filters produce a self-contained selection for galaxies above redshift 9 where we don't need any ancillary data, which is important because we don't know a priori where our pure parallel pointings will be. So in principle, we can identify galaxies even up to redshift 30. Our second science case is to complete the galaxy census at redshifts 3 to 7. So right now, our current state-of-the-art surveys have a hard time identifying dusty and quiescent galaxies above about redshifts 3 to 4. So here on the right panel, you can see 3 example SEDs of galaxies at redshift 4 to 5 that are either dusty or quiescent, and their SEDs, given what the Spitzer depths of some of the deepest Spitzer imaging that exists to date, it's hard to distinguish and select galaxies at these early times with these types of SEDs. And so the colored arrows are showing our minimum survey strategy for panoramic. And so you can see that we're going to get really good coverage of the SEDs for galaxies like this, like these types, and we'll be able to select and sort of identify them and characterize their stellar populations pretty accurately. So science case number 1, panoramic is going to occupy sort of a novel parameter space relative to GTO and ERS programs. So we're hoping to detect 80 new redshift greater than 9 bright galaxies, so brighter than L star, and up to 10 above redshift of 12. And an important component of this is going to be that with panoramic, because of our independent pointings, we are expecting something like 10% excess uncertainty on galaxies around redshift 12 due to cosmic variance, compared to more like 50% for contiguous fields of smaller area. And an important part of this is that we're also going to be capable of discovering rare intrinsically bright galaxies at redshifts of greater than 10 should they exist. Right now, there's open questions about intrinsically bright galaxies in the early universe. GNZ11 is an excellent example of this, where found in very small survey area and also very bright. It's unclear, this is much brighter and more abundant than expected from extrapolations from the luminosity functions and the model predictions. So it would be interesting to find out if these things are representative of early galaxy populations. So science case 2, completing the galaxy census of redshift 3 to 7. For quiescent galaxies, the abundances are totally uncertain right now. The model predictions span something like 2 orders of magnitude above redshift of 4. Surveys that have tried to identify galaxies above redshift 4 find a wide range of abundances. Probably some of this is due to selection effects, but we're hoping to put better constraints on the abundances of quiescent galaxies and sort of chart their appearance through this formation era, because we think these things are probably the relics of the reionization era. So here you can see where we're expecting to get with panoramic. We're hoping to get, depending on the range of model predictions, something like 30 to 200 massive quiescent galaxies from this early time, and these will make excellent candidates for follow-up spectroscopy in future cycles. Another part of completing the galaxy census is looking at massive dusty star-forming galaxies. So in particular, we're very interested in these recently discovered dark galaxies, which are dark right now because our infrared imaging is not deep enough, but with JWST, and this simulation is showing panoramic photometry in particular, we're going to put much better constraints on what the stellar populations of these galaxies are and better photometric redshifts. And so the ultimate goal here is to try to characterize their contribution to the cosmic star formation rate density above redshift of 4, and understand what level of star production is happening obscured by dust. So now that the cycle 1 allocations have been made, we have a better understanding of what the real panoramic survey will look like in terms of the cycle 1 parallel observation availability. So here on the left panel, I'm showing here the points show observations for cycle 1 that don't currently have parallel observations scheduled that meet our criteria for our minimum survey strategy. And on the right panel is showing the histogram of exposure times for these available pure parallel slots that Panoramic could occupy. And so our minimum was 1 hour integration time per visit. But what you see here is that a lot of these pure parallel slots actually have much longer integration time, so with an average of about 4.4 hours. And so if you were to take this distribution of exposure times to sort of, predict what the Panoramic survey will see, Panoramic will actually be sort of the perfect self-contained wedding cake survey strategy. So this is a plot showing just a redshift 12 luminosity function constraint. So that blue histogram translates into this red curve. And so you see that we are going to have a large area of shallow imaging to sort of probe the bright end of the luminosity function and distinguish between different types of evolutionary models for the bright end of the luminosity function. But we're also going to have a range of observations and pointings with much deeper imaging to sort of also probe the faint end. So, Panoramic was designed to do these specific science cases as a self-contained imaging survey, but in fact, it's actually going to produce a wealth of ancillary science possibilities. We're expecting to detect something like 2 million galaxies from our 0.4 square arc minute, 0.4 square degree survey. This is the expected photometric redshift performance for our minimum survey design, and we're actually going to get really good photometric redshift constraints even without ancillary data, even for a lot of these, even with only 6 filters. So our photometric redshift performance will be sort of comparable to what there was for candles, and so we're sort of expecting to create a legacy survey with a wealth of other science possibilities enabled by the good photometric redshift performance. So the Panoramic team is going to produce some publicly available data products from our survey. Our data is public immediately, but the science-ready data products will be coming out over the course of our survey. So we are planning to release science-ready image mosaics for each of our 150 near-cam pointings. We are going to create multi-wavelength photometric catalogs with photometric redshifts for each pointing. I forgot to mention that in the map of real parallel observations that we might take, some of those parallel observations will lie in well-studied ancillary or well-studied deep fields with ancillary data. And so some of our pointings are going to have also ancillary data in addition to the near-cam imaging. So I mentioned earlier that about 30% of our data is expected before the cycle 2 deadline, but we're for sure going to have all of our data set completed, and our plan is to get it publicly released in time for the cycle 3 deadline. And along with this, we plan to include stellar population modeling and structures, as well as characterizing field by field uncertainties. So one feature of our survey is that each pointing is gonna be very heterogeneous. So there will be a range of depths, a range of filter sets, a range of dither patterns. And so it's going to be important in order to do census observations or census measurements to characterize the completeness and selection functions and how the uncertainties vary field to field. So along with this challenging data set, we're going to try to make an automated near-cam reduction pipeline software that can go directly from, can handle all of these heterogeneous properties and go directly from pixels to galaxy catalogs on a relatively unmonitored and rapid timescale. So this is just a summary of the Panoramic survey. So we designed it to search for rare and red galaxies missing from our current galaxy census. It's going to be a large area-wide tier survey of 0.4 square degrees with independent pointings to mitigate cosmic variance. We have a minimum survey design that gets to depths of about 28 AB mag 5 sigma. And the real survey will create a perfect self-contained wedding cake strategy and yield excellent photometric redshifts for a wealth of ancillary science for 2 million galaxies. So thanks.
And thank you very much, Christina. Let's wait a little bit for some questions. So please put your questions in the Slack channel.
So I can start off with one of the first questions that we have here is asking if there's any synergy with Euclid or Rubin, and I guess any other telescope as well.
Yeah, I think there will be, I mean, both of those surveys will create wide area imaging surveys. And so, I mean, ours is going to be a little bit, it's going to be smaller than those facilities, but I think importantly, we're going to have this 2 to 5 micron that won't be accessible by Rubin or Euclid. So, so I think it's important to do a wide tier survey now. But sure, I think there's going to be plenty of science overlap, and we may even having this 2 to 5 micron imaging may be important for sort of informing those later surveys that will be able to probe much wider areas.
Great. I'll ask the next question. So regarding redshift greater than 9 bright galaxies, do you have any estimate of the contamination fraction for low redshift interlopers?
Yeah. Yeah, we studied this extensively while we were preparing the proposal. I think, so one of the things that we did was to try to integrate deeper in the bluer filters in order to try to minimize the contamination rate. I would have to go back and look at the original proposal to get some firmer numbers for you, but I can answer that question later, I think, in the Slack easily.
Okay, that would be great. That's all so far that's in the Slack. I'll ask one of my own. I was curious for the redshift, 4 to 5 quiescent sources. What do you think your stellar mass limit is for those?
Oh, so the simulations that I was showing was 10 to the 10.8, I think, in solar masses. I think, I mean, our depths would get us down much deeper to probably 10 to the 9, but I don't know off the top of my head the sort of how well we can say whether or not they're quiescent at those mass limits or not.
Right. Okay. All right. Well, thank you very much, Christina, for a great talk. If people have further questions, please put them in the Slack. With that, we will get our next speaker ready, who is Dan Coe. Dan, would you like to share your screen?
Yeah. Thanks for everything. Thanks for this conference, and it's great to be here. It's a great tradition I think you've started with these SAZERAC conferences, and I hope to continue next year, hopefully in person. It'd be great to see all of you. So yeah, I'm Dan Coe at the Space Telescope Science Institute in Baltimore, where I'm an astronomer. I also I'm a NIRCam instrument scientist, so I support all of you in your proposals, and then in the program implementation, and also the data analysis, which we're all looking forward to. And we're in Baltimore, which has been Cicada Central lately, so that's been a lot of fun. And all right, so let's dive in. So yeah, as we've been talking about, it's been great to hear about all these great JWST programs, and congratulations to everybody who's gotten time. And so 10,000 hours of observations are being planned for cycle 1. Over 2,000 of those hours will be public immediately, and we can hope to start seeing data around this time next year, assuming all goes well. So we've heard plenty of talks about the many blank fields and also lensing clusters that we'll be observing with James Webb. I'm going to focus on the lensing clusters in this talk, and I wanted to give an overview of the different observing programs. And so why lensing? One of the simplest reasons I can give you is I think that lensing will be the key to discovering the first galaxies with JWST. You also saw Evo show this. And this is my prediction given naive assumptions, but if the luminosity functions continue to steepen, there'll be many small faint galaxies. The lensing advantage will multiply even more at high redshifts. But this all remains to be seen, and it's going to be difficult to look through the cluster light. So we have to make sure our tools are up to that task. And the other main reason, of course, is lensing magnification allows you to see much smaller structures than you would be able to do otherwise. I borrowed this slide from Jane Rigby showing parsec scale structures in a galaxy at, I think, about redshift 2 in this case, and what it would look with and without lensing. So, all right, so the Windhorst, Roger Windhorst GTO program is observing 7 lensing clusters. I'm a part of that effort. And that's primarily near-cam imaging. And you'll see the top 3 of these, the frontier fields clusters, are also being observed by other programs, which I've shown here, including Chris Willett's nearest GTO Canucks program, and observing 5 of these clusters with NERIS to get spectroscopy. And some of these clusters are being observed by the same program or multiple epochs, which is great because they enable searches for transients, which include individual stars at high redshifts. So we might find supernovae or microlensing transits, unexploded stars within the first billion years, which would be very exciting. So far, we see a few examples here of individual stars observed at around redshift of 1. So here's a spreadsheet that you can screenshot of the various GTO and ERS programs. So and the different instruments, a lot of spectroscopy, also imaging. So far, I've covered these in the box here. What I haven't mentioned are the individual targets that are being targeted by these programs. And I haven't mentioned Jane Rigby's program yet. So I'm going to show those here on this next slide. So I had a lot of fun putting this together. These are images of the various strongly lensed galaxies that will be observed in cycle 1. This is Jane Rigby's program over here. Instead of the largest arcs, she picked galaxies that would fit inside the IFUs to study those in detail. Here you see the larger arcs. This isn't to scale, so I had some more fun putting all of this to the same scale on the sky. You can see the sunburst arc is the brightest galaxy on our sky, very brightly lensed and magnified. You also see a quiescent galaxy at redshift 2. Here's the brightest redshift 5 galaxy known, and the most highly magnified redshift 6 galaxy known. This is a more recent discovery from my RELIX program that my student Brian Welch will talk about more on Wednesday. At the bottom, you can see more typical sizes for these higher redshift galaxies, exceedingly small, all the way up to redshift 11. And these will all be targets in cycle 1. So here then are the observations of these galaxies. Evo gave a great talk about Uncover. Very exciting to have deep imaging and spectroscopy within the first year of a galaxy cluster. And these are all, there's NERSPEC spectroscopy for all of these at different resolutions. These programs are all observing with at lower resolution with the prism, getting the full wavelength range. And then there's other medium and high resolution observations. And most of these also have near-cam imaging. And apologies if I missed any. You could actually contribute. So I started a spreadsheet where I've been cataloging all these high redshift targets in the field and also in lens surveys. Please contribute. It's incomplete so far. I saw Christina also do a lot of this compilation in a AAS talk. Madeline could help me out with the quasars. Please, contribute to this. This is here for everyone. And so I'd like to also focus on my own programs. Programs to observe the most distant lensed galaxy known at redshift 11, and then also this most highly magnified galaxy at redshift 6. And I'll mention I'll be looking for a postdoc to help out when these data start coming in around next summer or fall. So these are thanks to large teams that we created for this, bringing in a lot of expertise that I didn't have to do this type of science. And similar observational setups, so near-cam imaging and the NERSPEC prism for both of these. And so with with that, for the Redshift 11 galaxy, for example, pretty standard filter set. I also added the Redis NearCam filter F480M to get the Balmer break at Redshift 11. I really wanted to add MIRI to go after O3 and H alpha, but my co-Is talked me down in terms of asking for too many hours. And also I realized that my proposal will be a lot different, hopefully in cycle 2, depending on whether we see 800 nanojanskis or 200 nanojanskis. We'll need different exposure times. So I look forward to that next cycle. And then here's an example of what we hope to see with the NearCam NearSpec Prism, the lines we do hope to see, giving you obviously the redshift and then some constraints on metallicity and ionization parameter and that kind of thing. And some of the things that we'll be able to really just nail with these observations, there's been a lot of uncertainty at redshifts, 4, 5, 6, 7, 8 for stellar mass measurements with the emission line contamination. Obviously we can do that a lot more cleanly with JWST, and at Redshift 11 we might see even higher specific star formation rates. So that's something that we'll measure very cleanly. And we will resolve, hopefully we'll spatially resolve this galaxy. The current upper limit is a radius of 80 parsecs. So it's a very small, it's the size of star forming regions in our own galaxy. We'll get down to 30 parsecs. Might just be seeing the tip of the iceberg with Hubble. And at Redshift 6, even more exciting, this strongly lensed galaxy. So Brian will talk about on Wednesday how he's done the lens modeling, and he sees 7 clumps, multiply imaged, and they're less than 10 parsecs in radius each, going out to about 500 parsecs. And for each of those individual clumps, we'll get these types of measurements for the metallicity, ionization parameter, things like that. We'll be able to measure metallicity gradients with all these clumps in a galaxy in the first billion years. So very exciting. And just to illustrate that these are very extreme clumps, smaller than have been seen before in other galaxies. Bound clumps at higher redshift, and we'll be able to do that science. Looks like I have a minute to go over the possible timeline for all of this. Launch followed by 6 months of commissioning. And so our observations, if they go the earliest they might go, we might get them around here. I've made all of our data public immediately. I hope to put out results quickly also for the community. Be attending. Hopefully I've put SAZERAC on the hook for 3 and 4 coming up here. And I'd say a few words real quick about, I want to figure out how to rapidly release results with public data. I think there is an issue with press releases that you might want to wait a little bit longer. But of course, with public data, other teams can come in and also put that on the archive. So I'm trying to figure out the best way to put out exciting results without going against those press release embargoes. And then just to say, I'm excited to see these data, already. So I've begun, simulating these. We have tools available at Space Telescope for all the different observing modes. And I plan to build a lot of this up too. I have a lot of the pieces in place, but I know other people are working on this, and I welcome your contributions from Christina and other people to make sure we have the best tools available for the community. And I will leave it there with my conclusions. And I'm looking forward to that we all are able to hit the ground running when the data start coming in next summer. So thank you.
All right, thank you very much, Dan. So please place your questions in the Slack, and we'll wait a little bit and see what pops up.
Yeah, there was lots of great stuff there, Dan. Can I make a request? And so some of these spreadsheets that you've built and some of the tools that you've built, maybe you can publicize these via one of the relevant Slack channels. There were so many great things you've been posting here. I kind of lost track of some of it.
Sure, absolutely. Yeah.
I'm a very big fan of open tools, so.
Yeah, absolutely. And I've also seen other people talk about their tools, and I'm looking forward to trying those out. tools, or you know, maybe we can make one.
Yeah, I can't remember if we had a channel already for tools. I don't think, maybe we don't at the moment, but yeah, you could make a channel tools. I think that would be a good idea.
Can I ask a question while we're waiting for maybe someone to show up in Slack? So Dan, one of your later slides was about like how to publish and press releases and competing teams and all that. So was there actually a suggestion you have there, or what are you thinking there?
No, I'm stumped, and I welcome your expertise. I almost emailed you last week. Yeah, what do you think?
I don't know. I try not to think about it. No, it's a really good question. I mean, I think, you know, there have been exciting new data sets released multiple times, and I've lived through it, I guess, at least once. And I think long term, the community sort of averages together things that get published over a couple month time period as, you know, the first result. So whether it's on day 1 or day 20, you know, probably not too big of a deal, but it's a good thing to think about. So maybe that would be a good topic for people to gather in one of the breaks and chat about.
Yeah, and I, just to be clear, I'm thinking of, you know, my idea is even more radical than you know, an archive paper draft. You know, what if you put something on the archive with just the result, you know, to just get it out there quickly if, you know, you want to support the community. But you know, but if you got to wait for a press release, then it would take longer. So yeah, I'm not sure how to reconcile that.
Yeah, I think we are kind of missing something, right? I think it's fair that people certainly running these big public programs should be able to kind of make a claim on some objects and kind of say, look, we found these interesting objects. Please go ahead and see if you see the same objects before you get to the point of having a formal paper. I wonder if there is something intermediate that we could explore. It's an interesting idea. Just imagine how many press releases there are going to be this time next year, though.
Right. Yeah, that's going to be exciting.
Yeah. Not seeing any questions. I'm surprised.
Well, people can take time to think about them and add them to the Slack, and Dan can check it later.
Yeah, I'll also join the Wonder Me later. I'll stick around after these talks, and you know, look forward to chat with people.
Cool.
All right. Well, thank you very much, Dan.
Thanks.
We'll move on now to the last talk in our session. Brant, if you'd like to share your screen. Our last talk is by Brant Robinson, and he's going to be talking about the JADES imaging campaign.
Hey, good morning, good afternoon to everyone. Today, I'm going to be talking about JADES, which is the Joint NERCAM NESPEC GTO survey. Thank you to the organizers for giving us the opportunity to talk about the survey. So JADES is a huge collaboration of many people. There are, as Stefano mentioned, more than 50 people in the collaboration. It extends over the entire globe, and maybe you could mute Dan. I sit on the steering committee, so there are 2 PIs, Marcia Ricci and Pierre Ferui. The steering committee is comprised of myself, Daniel Eisenstein, Roberto Maialino at Cambridge, and Chris Willott at Hertzberg in Canada. Dan Stark is the publication coordinator, and there's a large number of people both on the NERCAM and the NERSPEC teams contributing, and I want to recognize their contributions, as well as the crows outside my window. So there's a huge range of science opportunities with JADES NERCAM. Many of those science opportunities have been spoken about today. I cannot possibly cover those in today's talk. So I wanted to give people as much information about JADES as possible and to tell you a little bit about what we've been doing to date. JADES started as a collaboration more than 5 years ago. And so we've been meeting regularly and doing work together as a collaboration in preparation for launch. And I want to bring people up to date on that and let them ask questions if they have any. So to give you an overview, like I said, JADES is a collaboration of NERCAM and NERSPEC. There's a series of observations that are scheduled, hopefully, over time, starting with some NERSPEC observations targeted on HST, then some NERCAM observations, then NERSPEC targeted on the NERCAM observations. I'll show you that in just a moment. The depths, here I have the 5 sigma point source depths. We reach deeper than 30 AB magnitudes at F200W. So really, this is uncharted territory, and some of the other programs will also reach it. It's really a remarkable survey. It's about the deep area in JADES is about 10 times the size of the UDF at similar depths, a little bit deeper. So it will be very, very exciting from that perspective. So the way that the survey is planned, and hopefully it will be scheduled in this way. Initially, there will be some in Good South, some HST observations, some HST targeted observations with NERSPEC during that time. You see those in dark green. During that time, in dark orange, will be imaging with NIRCam in parallel. Then we will also do NIRCam prime surveys, this deep area that you see in dark red with NIRCam while exposing in MIRI in parallel. There will be some medium NIRCam prime observations taken with MIRI medium observations in parallel, and some medium NIRSPEC observations targeted on candles with medium NIRCam in parallel. Then 45 days later, roughly, we'll come back hopefully with JWST and target deep NIRSPEC observations on the JWST observations in the deep area of JADES, and also take some deep medium NIRSPEC observations with NIRCam in parallel in orange that you see there. We have a similar program. Oh, this is the total program. Stefano showed you this. This field rotation is completely nominal. It depends on when the scheduling occurs, approximately plus or minus 45 degrees, and it depends on the observations being scheduled the way that they're presented here, and not using another observing window, of which there are a few. Then later on, we plan to target JADES Goods North. So this will be medium NIRSPEC targeted with HST targets from candles, followed up with a medium NIRCam in parallel. And then we'll also do some medium NIRCam targeting with MIRI in parallel as well. And this is what we'll come back 45 days later, hopefully come back with the NIRSPEC targeted on NIRCam with NIRCam parallels off to the side, hopefully at an orientation somewhat similar to this. Again, it depends on the scheduling, whether or not this kind of field arrangement will actually be executed. And we hope that it is, so that the NIRCam observations that are taken in parallel, these orange fields, fall on the HST imagery in Goods North. So, we've been talking about these observations, what actually goes into processing them. There's a huge amount. So for us, we have to go through a NIRCam oriented pipeline. We have to produce images and mosaics and detect objects, produce photometry, measure structural parameters, do some initial SED fitting, and then we can feed that information to NIRSPEC to do targeting. They have to design their MSA, they have to acquire the data, and then there's some additional analysis. You can see it's doubled up here. We try twice as hard in JADES to do our analysis. So what we've been doing is doing simulations with Guitarra. This is the software produced by Christopher Wilmer at Arizona. This allows us to simulate the sky using an input catalog. And for this, we're using Christina Williams. I'll show you some of those simulations in a moment. We take these simulated observations and we mosaic them. We include distortion in these observations. I worked out the conversion between SciAF and SIP, so now we can use things like AstroPy, at least for NIRCam, to do our mosaicing and analysis. So we create a mosaic, very carefully keeping track of the error propagation. This is something that Sandro Tekello has worked very hard on. We do visit-based mosaics, and then we combine the visit-based mosaics into a larger mosaic. This produces an image, a flux image, error images. We get exposure maps as well. And that information is then fed into a pipeline that does detection. Let me show you some of these simulated observations. This is based on the Jaguar Mott catalog, Christina Williams catalog. This is a portion of the survey that you would see with JADES. This is a simulated F090, F200W, F444W image. And let me just zoom in several times so you can see the observations and the details that are available. We then have some kind of signal to noise ratio image that we stack together in a careful way, multiple different filter images from JADES. We then perform detection. This allows us to come up with a segmentation map. We can identify objects, and here you see the objects with their ellipsoidal isotopes shown. And then we record the information by measuring things using, say, SEP on the images as well. And let me just then raise a few issues I want everyone to think about. One is detection and deblending. This is an image of the segmentation map, and let me just zoom in a little bit. What's the best way of performing detection on these confused images? How are we going to do deblending? This is something that we're working hard on in JADES, but is not a solved problem by any means. We also have photometric validation. What's the best way to measure photometry in these crowded images? And we've been simulating this process from end to end in JADES and trying to improve our techniques. This is point source photometry. That's why it dips below the one-to-one relationship for very bright objects that are extended. Kevin Henline has come up with a new method for allowing us to inspect individual sources. So before we pass those sources on to NESPEC for follow-up, we have to fit SEDs to them. We have to know what redshift they're at. And we actually want to look at them in some detail. So Kevin has come up with a very a nice method to import all of that information from the mosaics and the SED fits and produce websites for each individual object in our catalogs, so we can go in and inspect them source by source to see how they're doing. We also have something called fits map. So once you have a very complex image like this and you want to lay down a bunch of slits, potentially how are you going to do that in a careful way? Well, we want to inspect the surrounding environment. We want to be able to interact with the data. So my student Ryan Housen has created something called fits map. This allows us to load in the images into a web browser. We can look at each individual image that we produce. We can look at combinations of the images. We can look at our segmentation map. We can overlay each individual catalog on top of the image. And then if we go back, we look at each object, we can actually click and interactively see all of the measurements in our catalogs. This software is public. You can download, pip install FitsMap and email me or Ryan, and we'll teach you how to use it. It's extremely helpful to learn how to interact with the data. It works on any data that's FITS-based in catalogs in standard format. So please let me know if you're interested in that. One thing we'll also be doing to try to augment our data is to do pixel level image classification of the JADES imagery. So Ryan Housen's created Morpheus, which is this deep learning framework for astronomical image analysis. And we scan through the images using convolutional neural nets and classify at the pixel level what the morphological classification of that region is, pixel by pixel. So we can tell where galaxies are disk galaxies, spheroidal galaxies, stars, compact or regular objects, or just background sky images. So it does do a form of detection as well. This is also publicly available, and please let me know if you're interested. So this will help us understand not just color relationships in the JADES data, but actually morphologically selected properties of galaxies as a function of time. So that will be very exciting. Okay, that's all I wanted to talk about today. So thank you very much for your time. I'm happy to answer any questions that people have about JADES. Thank you.
Thanks very much, Brant. So we'll wait just a little bit and see if any questions pop up in the Slack.
Yeah, my slides are available, by the way. You can download them. They're available on PDF. Hopefully other people can contribute their slides too for convenience. So going back to the question that was asked of Stefano about the release. So We would like to release some of the data. Whether or not, or the timeline for that release depends on how the data is scheduled. So as you've seen, for us to really optimize our survey, we have to come back with NESPEC targeted on NearCam imagery. There are really ideal times for doing that really enhance the science return of the survey. So, our goal is that if the survey is scheduled in a way that enables that science to happen, then we'll try to release some of the data as soon as we can. Unfortunately, with the slippage of time and the way the windows appear, I'm not sure whether that data will become available before the cycle 2 deadline. Our observations would have just been taken just a couple of months ahead of December 2022, which is launch plus 13 for the cycle 2 deadline. If we can enable that to happen, we will do so. That since Good South is being acquired first, the public data that we would release earliest would come from Good South.
All right, so we've got some questions there. Steve, did you want to ask
Great.
the first one?
Yeah, sorry, I was getting attacked by a bird outside. Brant has his problem with crows. I have problems with pigeons and seagulls. So regarding the source confusion, is this because JWST goes too deep and there are too many faint sources?
Yeah, it's hard for me in my heart to say that observations go too deep, but I think that's functionally what's happening. So if you go deep enough, then you start seeing the extended low surface brightness regions around galaxies, elliptical galaxies at lower redshift. The objects really do become confused. I don't have a number for what fraction they are, but you saw the segmentation map. The segmentation map is almost filled, and actually that's very difficult to do, to separate and de-blend out all of these sources, extremely challenging. So yes, in effect, there are many faint sources. There are many faint sources near bright sources. There are many bright sources that have extended low surface brightness features that then start to confuse the image. A lot of the pixels have detectable flux in them.
Thanks. The other question was not a question. It was just that people are excited to use the tools that you all are making.
So this is some way that I think JADES can really contribute back to the community. So, we're still working on our pipeline. Our pipeline is not yet public. A lot of these tools are public. FITSMAP is public, so please ask me about that. It's such a cool tool. It's so fun to be able to zoom in on the data and pick it apart and click on sources and see what their properties are. I also really think that something like Morpheus will be very helpful to the other surveys, and we're planning to collaborate. And I'm personally collaborating with Ryan in some of the other surveys, and we'll do our best to try to annotate these images to produce as much information in them as possible.
So there was a question that just popped up. It says, does the code do well at identifying lensed objects? I assume maybe that's for Morpheus.
For Morpheus, so we haven't worked so much on the lens objects. We did work on the Buffalo fields at one point, but we didn't pursue that much further. Those fields are extremely crowded. So we're still working on the performance of Morpheus in like strongly lensed fields. For individual lensed objects, or actually any of the tools, it's very difficult for us to say one by one whether an object is gravitationally lensed, if it's in the field, if it's lensed by a foreground galaxy lensing, or even galaxy lensing by some foreground protocluster or something. It's very difficult to do. So that's something we've talked about, but we haven't come up with a great solution for that problem yet.
All right, great. Well, thank you very much for this talk, Brant. Thanks to everybody who spoke in sessions 1A and 1B today. This concludes the first day of SAZERAC. So we will have our next sessions tomorrow morning US time or afternoon in Europe, same time, 13:30 UTC. And I believe the Wonder Me room will just stay open if people want to congregate there. Otherwise, we will see you all tomorrow. Are there any other logistical announcements, Steve, we need to make before we break?
The only other one is if you do have a recorded talk, then, and I know lots of people have submitted them via the Google form, they should now appear on the website, but be good to promote them via Slack, because I think people are more likely to see your recorded talk and interact with it if you promote it via the relevant channel on Slack. That's probably the best place to do it. But yeah, they don't automatically update via the website. So if you do submit it via the website, I'll try and do it every day and try and update them. So yes, Slack is probably the best way of doing it. But the website will give us this searchable list where they're all tagged. Yeah, I'm just saying I will personally join WonderMe myself for a little bit. If anybody wants to chat. It was nice catching up with people earlier and seeing small children and things.
All right, thanks everyone.